Okay, now just to finish off the uncertainty propagation calculations properly, it's a lot easier to do when I did it with a bigger class, and so we had more results. And so this one here was deleted. So you can see straight away the error with this is we do have a range of 5, but we don't have repetition of 5. And so we need that in order to get rid of anomalous results and still have a value. And so this is only done as one trial, which is an issue. I've already done the calculations for masses and moles and volume and this in the previous video. You'll see them again in this video. All the calculations that are done here as such. And so what I've graphed here is the moles versus the molar volume. Now you need to have some sort of graphical way to graph it. I don't know if there's a better way than this one, but you need some way so that you can indicate what all this mess is, because that doesn't mean much without a thorough analysis, whereas this can very easily show you, so it's meant to be 22.7, and the higher the moles went, the larger the error. We think, obviously the huge error in this is it's only done once, so we're not quite sure about the accuracy of where those points are. The overall accuracy of the experiment can be seen as far as where it is, how close it is. It should be on the line. I guess the precision is how far away it is. So this value here is getting outside the limits. Okay, so that's how you'd set it up if you did it as an experiment. You could do this as an SE, as a report. You'd just have a lot of columns. Maybe 15 of them, so you can get all done in 1 hour, maybe 2 hours to set up, put away and stuff. So you can get the 30-minute sort of incubation all done all at the same time. That's what you've got to think about when you're planning. Okay, now just to quickly look at the uncertainties. The pressure for water was plus or minus 0.01, and this is not the table I used, but you can see there's a plus or minus 2, so that's 0.2, and so that's where I get the 0.2 here and the 0.01 here. The pressure, the error on the mass, it measured at 3 decimal places. We tared it, then put the mass on, so you double it. Even though it's the smallest increment, you've done 2 measurements, one by tearing, one by measuring. The other errors, this particular tube was quite strange. It went up in 0.2 mils, so the error is correct at 0.1, half the smallest increment, and it's like a measuring cylinder, so we don't double it like you would if you're doing a titration with a burette. And that's all the errors. Okay, so as with the previous calculations, this was in the previous video. The only difference is you always use you're always trying to be accurate with your errors, so you're trying to find out where the largest error is, and so you'll purposely take the smallest mass used, because that'll give you the smallest denominator, give you the largest error. So that's the largest error on the mass. It's quite large actually. So if you're doing these things properly, you should always use a Mettler balance, which goes to 4 decimal places, and that will reduce your error by 10%, which is huge, which is pretty much the total error almost. What was the total error? Yeah, 10%. All right, reduce it down to 0.1%. Okay, so if you know there's errors at down here, which I'll look at in a second. So the next one is got to convert these things to percentages, because at the end of the day we're going to do times and divide calculations. So for the time being, we have the percentage errors on this. So that one there is actually a mistake, because I'm plussing or minusing here. It should be plus or minus 0.21 here. Because I'm plussing and minusing calculations, I add absolute errors. And so the percent error, it'll be interesting to see if this is any different. 0.021 divided by 99.16. And it'll be interesting to see what the difference is. So I'll just do that on the calculator over to the side here. So that's 0.21 divided by 99.16 times 100. It's 0.2. All right. That's going to be painful. All right, so I've got to correct that all the way through. Just remember to do that. I'll just highlight that for the time being. Okay, so this one here, I can decrease that. Sorry, that one goes there. Wrong place. All right. So I don't actually need to do those ones yet because that's done down there. Okay. So this one had that's a standard value that was taken from the from the thermometer, which went up in 2s. Okay, so that was a little bit strange as well, which I didn't mention before. That gives us a plus or minus 0.3%. That one I've already talked about. The only difference is we take the smallest volume again to get the largest error, so that's 0.5%. And so then we get the whole P1V1, so we'd have to get the pressure error, which is now 0.2%. We have to get the volume error, which is up here, temperature error, which is here, and then the volume error, which is over here. Okay, so because of times and dividing, now we add all the percentage errors, and so that'll give us a 1%, plus or minus 1%. Okay, now the final molar volume is this volume plus the number of moles, so that's the 1% here, to make an adjustment. And the number of moles errors up there. So the final one is 10.5. And so that will actually round up to 11. Have I made a small mistake? I don't know. The only good thing is for most syllabi, minor mistakes are overlooked, and usually a minor mistake like that, like a 0.1, it does round off to nothing. And it does again. It rounds off to 10. It has to be to 1 sig fig, so it's actually back to 10 again. So it doesn't matter, all those little minor errors that I did, and I think I did one before as well, it always comes back to the final number of 10, because it's very close to 11s and stuff with those errors. Okay, so I'll just change this, even though it's not significant, it's going to give me the same result in the end. 2.31 rounds off to plus or minus 2. Okay, so when you get your final answer, that's when you reduce your percent uncertainty to a sig fig. Then you'll times that by your final answer. So you only do this at the very, very last step. You do the 1 sig figs. And so that'll give us a 2.31. Everything's down to 1 sig fig. Okay, so that gives us up 2. So I have to round off my final answer to the 1's place. Often it's to 10s or 100s if I've done a better job on getting a more accurate balance up here and getting a smaller error. All right, and so the final answer is quite large. Is quite imprecise. It's 23 plus or minus 2. And so the answer is 22.7. It's close to 23, so 21 to 25 is my range. So I did get the correct answer. It is accurate, but it's definitely not precise. Would have been better to get it to 0.2 and then do more trials to maybe get a better average. Maybe you can get a 22.7 plus minus 0.1 would be much, much nicer, all right, to get. And so this is the errors I've asked students to get over several years, that we just keep adding to them. Surprisingly, this year is the real issue is actually not having enough trials, and we haven't actually got to that. As you can see, if you're going to do this graph properly and do this as a proper experiment to get a proper idea of what the real precision is, you're going to have to do more trials. And so things you might not have considered, I'll let you read through those. It's very comprehensive. This one was added this year because I actually saw it happen, which is quite unusual for it to separate and slip out of the tube. But it happens if you do enough of these experiments, you're going to see some of these small errors. Largest error would be obviously the balance, okay, in these calculations, okay? So that is useful for your exams. Maybe you're doing a data test or end of year exam, but certainly useful for your internal assessment science reports.